How's you? I'm on
It's my pleasure to introduce the next speaker, Professor Charlie Falco. He is a professor of optical sciences and physics here at the University of Arizona. And in addition to physics, he does other things, like he was the co-curator of the art of the motorcycle at Guggenheim Museum a few years back. And this was the fifth most heavily attended art exhibition throughout history. It went from Guggenheim to Bilbao in Spain, and Dr. Falco wrote the introduction to the book that came out about that exhibition. And he claims that the introduction that he wrote for that book has been read more than all his physics articles combined. But that doesn't tell you how many people read the art of the motorcycle, but it tells you how few people read his other articles. He is also well known for the Hackney-Falco hypothesis, and I'm sure he's going to talk about that today. So without further ado, I let Professor Falco tell you about his great work.
To slightly correct something that he said, I think more people have read that essay I wrote for the exhibition catalog than all my scientific publications. There's like 275 of them, but all of them combined by a factor of probably 100. So today, we're going to talk about something slightly different. We're going to talk about art and optics. I'll tell you who David Hockney is. I'll just give you one acknowledgement. Read these acknowledgements. Jose Sassian is one of our colleagues here in optical sciences. I'm not going to show you any of the work that he did. He did some ray tracing calculations early on that I'm not going to use in my talk today, but it was very helpful at the time. In fact, I'm going to spend half my talk. Some of you heard my talk last year. Less than half of what I'm going to talk about today you heard last year, and most of it is going to be the end. But all of this will be introduction to what I'm going to be talking about of things related to what we're doing in optical sciences and what we're planning on doing in the future. So I'm going to give you an introduction, and I'm going to jump and show you evidence only in one painting, some of the evidence in one painting that shows artists 200 years before Galileo were using optics to project portions of their images in the most famous paintings that you've ever seen. And I'll only show you one example, but I purchased at no small expense to myself that domain, art-optics.com. And if you go to art-optics.com, you're all bright people, you'll remember this. It'll bounce you to the university, to the OpSci webpage, where you can download PDFs of all of our publications, and you can learn much more about anything that I show you. If you're I'm not convinced by a particular piece of evidence because I've gone too fast today, go and download the PDFs and you can read it. Yes?
Maybe you can also remark that Charlie's talk from last year is available on the Winter School and Workshop website.
Oh, I didn't know that.
You'll learn something in every talk. This is really good. So I'm going to show you a little bit of evidence, and I'm going to talk about where this is all going in the future. So as an introduction, first, who I credit as the co-author, David Hockney, two respected dictionary of art and artists, most critically acclaimed British artist of his generation, his etchings, deftest of the century, perhaps the greatest of modern portraitists. If there were a Nobel Prize in art, David Hockney certainly would be on the short list to be considered for it. He's a world-class artist, and as a result, I've been working with him for the last 15 years. I've learned a lot about imaging from, if you will, one of the world's greatest
David Hockney, our most celebrated living artist.
He is considered to be one of Britain's greatest contemporary artists.
His originality and skill have ensured his success from the beginning of his career.
So he's a world-class artist, but for our purposes, the thing that's most important about all of this is...
I admit, for instance, I am interested in pictures. I keep saying this. I'm interested in how you make pictures.
So throughout his career, he's been very interested in imaging. How are images created? How are they transmitted to people? How do our brains process the images? All of these things came into play in the discoveries that we made. And then a technology that the professors in the room will remember, you guys won't, is there are these things called fax machines, where you would take a piece of paper, and it's actually pretty magical. Put a piece of paper in, it would suck it through, and then paper would appear on the other side of the world and look just like the paper you put in there. Nobody really understood how that worked. But in the first few months of our collaboration, we'd exchanged a ream of faxes. So 500 pages of faxes. By a few years later, 1,500 pages of faxes. And the last time I took a picture, we'd gone through 6 reams of faxes. And some of these, by now, David has started using email and sending PDFs of his work. And so I would print them. So some of those. This, by any measure, is the most intense scientific collaboration of my career by far that I had with David Hockney. And just to give you an idea of the implications of the discoveries that we made, that our theory shakes the foundations of art history. It shows that optics was used at the dawn of the Renaissance. It is responsible for the creation of the iconic images that all of you are aware of and you've seen. And so that's sort of a pre-conclusion of where we're going with this. I'm going to show you one example, one kind of analysis we've done on paintings as background to what I'll talk about for the rest of the talk about where this is going. And it's a painting by Lorenzo Lotto, 75 years before Galileo. Art historians, if you ask them, could optics have been used to project images? An art historian might say, well, it's possible after Galileo they didn't do it. We're sure they didn't do it because that would somehow impinge on the fact that we believe they're geniuses. But in principle, somebody could have done it at the time of Galileo or later. What we've shown is that they did it 200 years before Galileo. So this is 75 years before Galileo. David Hockney, at the time I'd met him, had been interested in whether optics could have been used. And he characterized things as paintings could have been produced by eyeball. By that I mean, if I wanted to paint Professor Mansurpur, I might kind of hold my thumb up for a scale and kind of paint around. And he would call that eyeballing, as opposed to optical, where I project his image and I trace part of his image. I fill in pieces that I want without tracing. But somehow optics was used. So he distinguished between these two. He collected all the paintings that he thought worthy of further consideration, color photocopies of them, if I magnify this, and he organized it like Mendeleev organized the periodic table. Figured out how to create the periodic table. Chronologically, with paintings from Northern Europe on the upper wall, Southern Europe on the lower wall. Trying to figure out if something happens, if there's a transition in realism, does it happen first in Northern Europe? Does it happen later in Southern Europe? Trying to connect this all together. One painting in particular caught my eye when I visited him. And it's called Husband and Wife. This one 75 years before Galileo. And there's various things that when you go to that website I told you about, which is, what's the URL for it? art-optics.com. Some of you said dot. No, art-optics.com. And some of you are dyslexic, so I also purchased optics-art.com. So there's really no excuse for you not to be able to find the stuff. Seriously, I did both. That if we look at that tablecloth, it's actually a rug, and if I magnify it, it goes out of focus. Is there anything, so what? We've all seen countless photographs. They go out of focus. The wine bottle's in focus. The car out there is out of focus. No big deal. Well, if you had never seen a projected image, and a photograph is a projected image, you would never have seen an image that's simultaneously part in focus, part out of focus. I look at Masood, he's in focus. I look back at Poole in the back row, he's in focus. My brain doesn't bother telling me that in going between those two, that it's caused the muscles in my eyeballs to contract, to focus on both, and then in my brain construct a overall composite where everything is always in focus. That's how we see things. So the fact that this, goes out of focus is a first, actually pretty substantive clue that optics is involved. Jumping ahead and not showing you lots of analysis, I've created there a octagonal pattern with a scale that we're really not going to talk much about today, but everything is done to scale. And what I'll do is I'll correct for perspective, and I'll lay this on top of the carpet, and we'll see if it fits. Because if I'm going to claim that the octagonal pattern in the carpet is it goes out of focus because of optics, seems like it should fit. Am I correct? No, I'm wrong, and you're all wrong. Because when I put it in color, when I put it on top, well, does it fit? No, again, you're wrong. Yes, it fits great. Look at this, perfect agreement. Any number of scientists, the professors in here, have been forced to, they've got some data, and they've got to go to a conference, and the data doesn't quite work. So they go to the conference, they go, look at the perfect agreement that I've got. And then when somebody in the audience says, yeah, but it doesn't fit at all, you say, but you've forgotten. This is when you project a image of a fairly large object at large magnification, the depth of field is really small. So I've had to simulate the depth of field with Photoshop. It's semi-in focus with a single element piece of optics from the 1500s. So we're not going to get perfect Nikon-like definition. Let me trace in the part that's in focus. And now I have to refocus to focus back there. If I focus on Masood again, Poole's moved, well, he's still further back. Counterintuitively, if I want to focus on Poole Yesen, I have to pull the lens toward me to focus on something further away. The lens is now further from the scene. Everything in the scene is smaller, and it fits. It doesn't fit up here, but it doesn't matter. I've already copied that in. Out of focus, I do it a second time. I refocus, and I get the whole painting. To analyze this, there's, sorry, I'm not going to show you that. There's the painting. I have actually a meter stick built into the painting. There's a woman in the painting. The distance across her shoulders is 10 inches. The distance across a real woman's shoulders is 18 inches. I know that because I have a wife and 2 daughters. So I have 3 data points. In the land of the dataless, the man with 3 data points is king. This is more data points than existed in all of art history up until this time. That says the magnification of this image is 0.56. I now know the magnification of the image. Nice regular structure. Seems to go out of focus somewhere between 5 and 9 repeats distances in. I'm not going to talk about this today. You've got to go to my website to learn about that. So I've got a depth of field in real units. We have these equations from geometrical optics that relate the focal length to the distance from the lens to the subject, the lens to the canvas, and the magnification. There are 3. The magnification in the front we've just determined based on my 3 data points is this. The depth of field we now know because of where it goes out of focus. There are 3 regions, so I've got 6 equations and 7 unknowns. What does that mean? 6 equations. That sounds vaguely familiar. What are we going to do with this?
This is it. That moment they told us about in high school where one day algebra would save our lives.
So we now remember. Our algebra teacher told us this, and we didn't really believe him, or her. We'll use algebra. 6 equations, 7 unknowns. We make one assumption. Everything else follows. I'm going to make the assumption that the distance from the lens to the carpet was about 4 feet. Couldn't have been 20 feet. Couldn't have been 20 inches. So that's my assumption. I put error bars on that. And once I do this, I get all the depths of field, all the focal lengths, and it all follows. There's no messing around. And I'm going to just point out, geometrical optics says that if a lens was used, there has to be 3 regions. There have to be 3 regions. And we know what the focal lengths are and the magnifications are. And jumping ahead and not giving you the algebra, that I calculate from algebra that the focal length, when I went from that blue region to refocus to the green region, should have changed by 12.6%. I measured at 13.1%. It agrees to the laws of geometrical optics to 0.5% accuracy. We don't normally in science actually do experiments to 0.5% accuracy. We don't need to. If you work at the National Institutes of Standards and Technology, you do, but normal people don't. If we move to where we go from the green region to the red region, the magnification changes by a different amount, but we calculate a different amount, and it again agrees to better than 0.5% accuracy. So we're not saying that lenses are the way to get perspective right. We're saying lenses is the only way they could have got the perspective wrong in precisely to 0.5% accuracy, the way they got the images wrong, if you will say. And so here I had a master's student in art education who reproduces. Take the octagonal pattern to life size, and what he's going to do is he's going to project that image through one lens of a pair of spectacles or reading glasses and onto a piece of clear plastic. And when he's all done painting it in, he'll take that clear plastic and he'll overlay it on a copy of the painting that is at life size, and we'll see if it fits. So this is what he's going to do. That image is projected onto John's easel, onto the clear plastic, and he'll paint the region that's closest to him first, using the same colors. He'll use blue to paint in that region, jump ahead and finish that. And then when it comes time to do the next region, it's completely out of focus, so he's got to pull the lens toward him, reduces the magnification, you'll see it come into focus. So now you'll paint that in the green, same color scheme. And you'll have to do it one more time after he jumps ahead and finishes that. Finish the region. All done with this. You'll take that life-size projection, put it on a life-size copy of the painting, we'll see if it fits. And it fits perfectly. This is how and why it looks that way. And so we made discoveries about a number of paintings. We published this. The European Science Foundation organized, there's been 3 international conferences about this. And so read what we've done, and here's what CBS says.
Here's what's so revolutionary about what you're saying. You're saying the history of art, the history of the Renaissance, is the history of optics.
I am saying
I know that, and you're blowing everything up. You're blowing everything that all of us who took art appreciation studied, all the art historians have written, and you're saying you're all wrong. It's all about optics.
Yeah. Art historians don't like us for this. Okay, so now we've shown that the artists have used optics and lots of other examples and stuff, but where does this go? So this led me to start thinking about other ways of applying optical techniques to art, to understanding art. And I'm only going to go over this kind of a few examples right now. Paintings on canvas or wood, the way they were made, and still are made largely today, is a white layer of gesso is put on. So the artist starts out with just white in front of them, and then puts pigment on. And it turns out the pigments are typically to say 20 microns thick. And this turns out to be very handy because when you shine light on well, if it's black, it absorbs everything, so nothing comes back. That's why it's black. So light is our visible light plus infrared, which we can't see, but we're going to make use of it in a minute. If we shine the light on a blue part of the canvas, well, it looks blue because the blue light comes back. So here, green. Red, it turns out, some greens and some reds, the infrared actually penetrates all the way to the gesso and comes back. But we can't see the infrared, so we don't know that. But a regular camera takes a visible bandpass filter and puts it in front of the sensor because the sensor in your camera does care about infrared. It does, the silicon is sensitive to the infrared, so we've got to get rid of it. The infrared is blocked. Let's take that and instead replace the filter that passed visible and blocked infrared. Let's only let the infrared through. And if the artist had put some underdrawing, like a paint by number, wrote, paint this region green, and then or paint that region red, and then painted over it, nobody has ever seen where he wrote, paint this region green. And I'll say he because every artist we've been able to show used optics was a male. So in this case, we can't find any. There weren't that many female artists at the time, but every place where we've got optical evidence is a he. So we'll see if we can find anything under there. Now, people have used it. Here's fairly recently, a scanning device, a scanning camera aimed at a painting. The scanning time for this is 3 hours per square meter. If you look, there are 300,000 paintings in the Louvre. If you did 2 a day, because it's a 6-hour working day, they're French, you have to have a coffee and a cigarette, it would take 400 years to scan all the paintings in the Louvre. So I developed a camera, which actually the capture time is a fraction of a second. So I could take infrared photographs of every painting in the Louvre in a year, which makes it realistic. And it's portable. This is not, I would call, portable. So let's see how well this camera works that I developed. This is a blob of red paint, obviously. With a visible camera, I'll take my visible camera off my tripod and put the infrared camera on, take the same picture in the infrared, and this is what I see. So maybe there's hope to see something with this. So I took this camera there's our painting, to the Hermitage. The film crew was filming this.
It's really easy to see the infrared. This shows up beautifully.
We're going to enter our story again in a few minutes. So there's that painting in the visible, taken in the Louvre. This is not from a textbook or something. This is a photo I took myself, and you can tell because there's some kind of funny, darker pattern on top. And what that is the painting's in a very ornate, thick frame, and it's lit from the top and from the side, the top by lights and from the side by windows, and that's the shadow of it. So a lot of things I could tell you about this, but notice here he's wearing black, she's wearing black. We'll just look at those at the moment. Now I'll take a picture in the infrared. He's wearing black, she isn't, and there's something going on here. In fact, there's a lot going on here. If I look at that central octagonal pattern in the infrared, a lot of the visual clutter is taken away. And what I'm going to do, in a region that's only 2.5 inches long, less width than the width of your iPhone, I'm going to show you that the artist has 3 regions. 3 regions because he had to refocus twice. Same color code as before. There's the blue. Let me bring this over to this part. And I only care about this central pattern, so I'll just block that out. This looks traced. After optics says he would have had to refocus, immediately it looks messed up. If you take a geometrical pattern and you reproduce it at 13% different magnification and you try to match it up, it doesn't match. And that's what Lorenzo Watto, to his dismay, discovered in 1536 or whatever. So it's out of focus. And he's had, it's it's out of registry. So he's got to kind of mess around to try to make it look realistic. Starting to look realistic, he has to refocus again, and he gives up. So if we see things in the infrared that we couldn't see in the visible, and it teaches us something about artists, maybe other wavelengths would be of interest as well. And I'm only going to just to motivate this show, I developed an ultraviolet camera. So multispectral imaging, the idea over wide wavelength range, because the pigments that we're trying to study all have different kinds of optical properties in different wavelength range, will teach us different things. So it'd be nice if we have to have a camera that's the size of this desk. It's less useful because you're probably not going to get the Louvre to send you the Mona Lisa to measure in your lab with your camera. You might be able to get them to allow you to bring your portable imaging system to the Louvre to take a picture under supervision, after hours. So portability is essential to do stuff. Another technique, Raman spectroscopy. In this, I just looked for a quote last night, offers the possibility of fully non-destructive analysis. I should say, that's also an advantage. If you get the Louvre to let you show up to do something to the Mona Lisa, and then you go, oh, by the way, this is going to be a destructive technique, then they're going to stop you at that point. So it has to be portable and non-destructive, and Raman spectroscopy might work. And here's a schematic of a Raman spectrometer. Really trivial. Laser shines through a filter, hits your painting, bounces back, and you measure with the spectrometer. Like John Hayes said yesterday, that you can have something that seems like a simple system, but when you actually try to make it work, things get a lot more complicated. And so I actually designed and built a Raman spectrometer this fall. And this trivial bit only took a couple of months to sort out all the details to make it portable. The reason is you need a laser with stable intensity so it doesn't vary with time. This transmitting filter has to have extremely narrow bandpass because lasers, this particular laser looks green, but it's actually got a couple hues of green. The primary bright laser wavelength is a few nanometers different from a weaker but still fairly strong signal. And you've got to get rid of those other weaker signals because the scattering from the sample is extremely small. It's like about a factor of 1,000,000 times down from the main laser line. So you've got to block the central laser line. If that central laser line gets through, it's just going to swamp everything. So you've got to get rid of it. Your blocking filter has to have a high rejection. And the spectrometer has to be high resolution, wide bandwidth. Those things don't go together. They don't naturally play well together. High resolution usually comes with narrow bandwidth and vice versa. Low noise, portable and rugged. And portable doesn't mean that I could take it from Poole's lab down the hall to somebody else's lab. Carefully. It means that somebody at TSA is going to look through your suitcase and go, what the hell is this? And knock it around, and you're going to have to, if you're going to carry it someplace. So it has to satisfy those requirements. I just grabbed this out of a book. The reason why you want to do all of this stuff is because Raman gives you chemical information, tells you about the chemicals in the paint, and so you learn about this. This is the world's largest art museum, the Hermitage in St. Petersburg in Russia. And it would be nice if we could, study their paintings. This is my portable visible spectrometer I carried with me. Actually, TSA sometimes has problems with this spectrometer. But so far I've managed to get it through security. So we've been to St. Petersburg. We're developing with the St. Petersburg State University of Information Technologies, Mechanics, and Optics. They changed their name. They just call themselves ITMO now. In fact, the origins of this institute go back to the Tsar. This was the Optics Institute of Russia. And we're developing a curriculum with these people and we've got to the point, my next trip there will be in June to give a talk at the Hermitage, where we will use the Hermitage as the teaching laboratory for the set of courses that we're developing here, which is pretty unique, you have to say. So to summarize, we've got overwhelming scientific evidence, all of which is in the web pages that you hopefully remember, art-optics.com, that fundamentally changes our understanding of art of the last 600 years. The photographic glyph is post-medieval. It comes from optical projections. Human vision system has evolved over 60 million years, but only the last 600 years have we actually been projecting images. And we're creating a joint program here in optical sciences with ITMO University where we will have, which we've made these arrangements, we'll have the world's largest museum as the teaching laboratory for our students who are interested in this. So with that,
this is the end.
I'll end my talk.